Thank you for coming. As usual, I'd like to acknowledge that we're meeting on the lands of the Ngunnawal people here in Canberra and acknowledge their connections to country. So I was asked, and I was very pleased to be asked to introduce Kial Stewart today. So Kial is one of our continuing faculty here at Earth Sciences. He actually did his PhD here many years ago with Ross Griffiths. And then went over and did a postdoc at Johns Hopkins University in Baltimore, working with Darren Waugh, before he came back to Australia, to UNSW initially, and then across to ANU, and has been here for quite a few years now. So Kyle does an extraordinarily broad range of things, both in terms of the topics he looks at, but also the methodology he uses. So he's rather unusual in modern climate science in that not only does he do numerical modeling work, but he also does physical models in the laboratory of the climate system, both ocean and atmosphere. And so that in itself is broad. It spans from anything like the melting of Antarctic glaciers, the formation and melting of sea ice, through to climate modes of variability, so the ENSO oscillation in the laboratory, and through to the stuff he's going to talk about today, which is Rossby waves informing Rossby wave dynamics and how they influence our future weather and what our weather is going to look like in a short time. Yeah.
I think you're muted them. So.
Oh no. How do I fix that?
You're fine. I can hear you.
Can you tell the story about the medal winning?
I'm going to get to the medal winning. Yep. Yeah. Okay, sorry, Zoomers, if you couldn't hear. I'm not going to repeat myself, but I'm just introducing Kyle. Kyle does this extraordinary breadth of work. He also, in terms of, in addition to the research work he does, he's very well known for the amazing outreach work he has engaged in, which has included these fluids in 4K videos on YouTube. And some of these are fundamental fluid videos that have 30,000 views, which is quite impressive. And an acknowledgement of some of this amazing work he did in this space was last year he received the Outreach Award of the Australian Meteorological and Oceanographic Society, which is our premier Australian society in ocean, atmosphere and climate. So that was a great recognition of these materials that Kyle produces from the laboratory, but then uses them and spreads them far and wide to be used in teaching programs all the way through from school to university and beyond. Rodri wanted me to talk about Kyle's other achievements. So Kyle is also a former Olympian. He's probably, I think, would be the only person in the school who has an Order of Australia and is a former Olympian, a gold medal winner. So you can talk to him about that at some point if you like. Cycling.
See?
Okay. I think I've covered everything I need to cover. So I will hand over to Kyle.
Thanks. Thanks, Callum. So I'm going to be talking about some Rossby waves. I'll start out by actually trying to tell you what they are. So this is null school, Earth null school. If you haven't seen this website, please go and check it out. What we're looking at here is it's formed from reanalysis. This is probably earlier today sometime, and we're looking at surface winds. This website ingests reanalysis and then plots it up in this kind of fancy way that I've got here. And a lot of you guys are oceans people. This is what the surface of the ocean looks like, just to give you a sense for the different scales of dynamics of motion that we're actually looking at. A lot of you are familiar with the size of these things. These are eddies. These are on the mesoscale. In the atmosphere or in the air, the mesoscale is quite a bit bigger and it's quite a bit faster. Now, if we go from the surface up to about 500 hectopascals, which is probably about 5 kilometres up in the air, and I'm going to change the projection here so that we can actually see it as as a latitude, longitude sort of thing. These are the waves that I'm talking about. These are waves that are riding on the jet streams in the southern over the southern hemisphere. These are Rossby waves. That's what I'm going to be talking about. Okay, so now we'll get. No, this is reanalysis. I'll explain what reanalysis is pretty soon. But yeah, that's reanalysis. These things don't exist in simulations. Okay. All right, so that's what we've just been looking at. This is an animation of it. So these are the Rossby waves that we're interested in. They, in terms of like what I'm going to be sort of presenting and showing today, I'm just going to give a quick overview of what they are, why they're important, some very basic physics of Rossby waves, the approaches that we take to studying them, and then some of the science that we've actually been doing with them recently. So how they're going to change with climate change, how in hemispheric differences in Rossby waves, and then seasonality. Okay, so I'm hoping that I've kind of covered like what they are. It's these things, these big wavy, like they're continental-scale waves that exist in the atmosphere. They dominate the weather that we experience, particularly in Southeast Australia. And why they're important? We can pick any number of different metrics to sort of answer this question of why Rossby waves are important. What I'm going to show is a couple of different ones. So climatology, rainfall. So this is the rain that we depend on for filling our dams, for filling our reservoirs, for drinking water, for agriculture, for watering our crops, for cooling our data centers. This is the rain that we depend on for those processes. And what Chen Hui has done recently is separate out like where the rain comes from based on different weather systems. And this one here is our Rossby waves. So this is climatology for summer, and over Tasmania and Southeast Australia, particularly Victoria, we're getting like maybe 30 or 40% of our climatological precipitation from Rossby wave dynamics. Go to winter, and this now becomes more than 50% of the rain that we get. Like the climatological rain, the rain that we use to plan infrastructure is being used, is over 50% of that is coming from these Rossby waves, including all of the snow. Like all the snow that, like when Australia, when the Australian Alps don't have a good snow season, it's because we don't have a good Rossby wave season. That's climatology. Extreme rainfall is also another thing. The signature of Rossby waves in extreme rainfall is even more prevalent. Over 80% of the extreme rainfall is driven by Rossby wave dynamics, which you can kind of see here. This is over 80% of this sort of stuff, is particularly over the Southeast Australia. So this is extreme rain. The signature of Rossby waves is also in heat waves over the Southeast Australia, bushfires, and it's also in northern monsoons. And this is also reanalysis that I'm showing here. It's composite averages. I'm not going to go into too much detail about what these are, but I just want you to recognise these as wave signatures. These are wave packs. This is positive and negative anomalies like leading into, like preceding some event. That's what the wave signature looks like in these metrics that we're looking at here. The bushfire signature is actually, like bushfire weather is it's a real thing. It's like where you've got these waves that are able to actually sort of start to get elongated in the north-south direction. You're able to get very hot, dry air being blasted across the interior of the country and then impacting onto the eucalyptus forests in the Southeast Australia. So all of these major bushfire events have Rossby wave dynamics associated with them. One of the classic Rossby wave impacts from the major bushfire events is the subsequent passing of a cold front, like a very extreme cold front. So some of these cases, you might remember these classic photos of firefighters cleaning up after a bushfire has come through and it's actually snowing. Like the temperature has dropped over 20 degrees, and it's because you've got these like huge big cold fronts that sweep past, immediately following these bushfire conditions. So in terms of like their importance, very quickly covered some of the aspects to Australian life that why Rossby waves are important. What I want to do now is just cover a couple of the dynamics, like give you a bit of a sense for some of the physics behind Rossby waves. And in order to do this, I just need to get two concepts across. One is standing waves and one is potential vorticity. And I'll try to do this quickly. So imagine if we've got flow, it's flowing across the board here and it's flowing at some speed u. If we're in the lab, I'd actually show you this. We've got imagine we've got a wave and the wave is sort of flowing in this, or it's propagating in this fluid, and the wave is trying to flow against the fluid. If the wave speed is, if the flow is going slower than the wave speed, that wave is able to propagate upstream, okay? Now, if the wave is going faster, if the flow is going faster than the wave speed, the wave is going to get vectored downstream. Now, if the wave is equal to the flow speed, that wave is going to become stationary. That's a standing wave. Okay, that's a pretty simple idea of what a standing wave looks like. But in the real system, it's turbulent, and there's waves at all length scales and all time scales. And there's flow in the background, right? So sometimes these waves, the wave speed will depend on the wavelength or the frequency of the waves. So there's actually a spectrum of wavelengths and there's a spectrum of wave speeds in this system, so that when you take a long-term average through time, what you'd actually start to like spike out are these standing waves, these waves that have the right frequency and the right wavelength. They're traveling at the right wave speed, so that you actually are able to get like a coherent packet of waves averaged through, like time averaged through this massive turbulence. And to me, this is where all the interesting stuff in Earth's climate happens, when the wave speeds match the flow speeds, because you actually get an opportunity to pump energy in to a specific wavelength and a specific frequency. This is where we're actually able to scale energy up into these particular scales and see some of the really interesting dynamics. So that's standing waves. That's what I'm going to be coming back to. The other concept I wanted to get across is potential vorticity, and this one's going to be tricky, but I'll try to do it. So imagine you've got a puck of fluid, and it's got some thickness and some diameter, and the fluid is spinning. So it's spinning about its axis. We would say the fluid is spinning relative to its surrounds, and so we would call this relative vorticity. So the fluid is moving, in some direction, and it's spinning relative to its surround. This is relative vorticity, and we can quantify relative vorticity as the change in the horizontal speed across the diameter of this puck. Right? It's literally a gradient, a horizontal gradient in the horizontal velocity. So we can change. This is how we would quantify the relative vorticity. Now, if you take that puck of fluid that's spinning and we stretch it, so we increase its height, through a conservation of volume, we're going to be bringing the outside of the fluid in. We're going to be increasing its spin. So we're going to be increasing its u, like its velocity. We're increasing the velocity difference across the puck. We're also decreasing the diameter. So we're increasing the top number and we're decreasing the bottom number. We're going to be increasing the relative vorticity of this fluid. And I'm hoping that you are able to intuitively convince yourself that there is going to be a relationship between how thick we make this fluid and how much we increase this relative vorticity. This is actually an assignment question from our third-year climate dynamics class. I'll leave it to you if you wanted to do it. But there is this, this conservation between the relative vorticity increase and the thickness increase. And the neat thing about this is that it's actually reversible. So if we take that stretched fluid and then we squash it back down again, this process reverses. And so we can just keep doing this stretching and squashing of the fluid and having it increase and decrease its relative vorticity. So this is a conserved property of fluids. Okay, so we're going to take that idea. Michael.
Is this like when a dancer kind of it goes inward and spins faster?
Yeah, that's the... That'd be the conservation of angular momentum. And yes, it is related to that. And I'm hoping you, if you were to do this homework exercise, you would lean on conservation of angular momentum and your intuition of that to help you with this exercise.
Challenge accepted.
Okay. So hang on to that idea. And now think about fluid on a rotating Earth. So Earth's spinning, Earth's rotating. Fluid is always spinning, even when it's at rest with Earth. It's still spinning. So the spin of fluid on Earth, we can think about it. We've got to actually think about how Earth is spinning. And if we look at Earth, it's always, the sun's always rising in the east and setting in the west. If we look at Earth from below the South Pole, Earth is spinning anti-clockwise. If we look at Earth from above the North Pole, it's spinning, sorry, I said anti-clockwise, it's spinning clockwise, it's spinning anti-clockwise. Okay, so Northern Hemisphere spins differently to the Southern Hemisphere. It's not a step change at the equator, it's a slow, gradual thing. So it goes from fast and clockwise at the South Pole to fast and anti-clockwise at the North Pole through 0 at the equator. This is planetary vorticity, and it depends on where you are on Earth. It depends on your latitude. By convention, we call it F, which is the Coriolis parameter, and it's positive in the Northern Hemisphere and negative in the Southern Hemisphere. So planetary vorticity, that depends on your latitude. If we think of a parcel of fluid on Earth and think about its relative vorticity, the thing that's important is the total vorticity, or what we'd call the absolute vorticity. It's the sum of the planetary vorticity, so your latitude, and the relative vorticity, which is this concept that Michael's talking about. So we've got the absolute vorticity, which is going to be the sum of the planetary vorticity and the relative vorticity, and the ratio of that absolute vorticity to the thickness of the fluid is our potential vorticity. All right, that's the second concept that I'm trying to get across. This potential vorticity is arguably one of the most dynamically important aspects or components to fluid dynamics. It's it's the ratio of this absolute vorticity to the thickness. It gives us a three-way balance that needs to be conserved at all times. It gives us the ability to actually time-step fluid equations. If we change one of these terms, we have to have a change in one or two of the other terms. So that's potential vorticity, and that's the second concept that I was trying to get across. Okay, so we're going to take these concepts of standing waves and potential vorticity and look at how they affect atmospheric dynamics on Earth. So if we think about our planetary vorticity, F, and we've got contours of planetary vorticity, which is just our latitude, and think about a column of air that is at Canberra here, say it's got some sort of thickness, and we perturb that northward, say, but we keep the height of this column as we've perturbed it northward constant. That fluid is going to go to a different planetary vorticity. Through the conservation of potential vorticity, it's going to need to increase or change its relative vorticity. So it's now spinning relative to its surrounds. Once it's spinning relative to its surrounds, it's going to be sheared by its surrounds, and its surrounds are going to actually try to send that fluid back to where it came from. Okay, so it's going to return to its initial latitude, but it's going to have a vorticity anomaly because it's been sheared once it went north. So it's going to tend to overshoot and go south. Once it's south, it gets sheared in the opposite direction to what it had when it went north, and again, it's getting pushed back to where it came from. Once it gets back to where it came from, it's going to overshoot again and keep going. So this oscillation between going north and getting sheared and going south and getting sheared is you can think of it in terms of a spring, like the spring here being the background gradient in the potential vorticity. The spring here has a restoring force that depends on how far you are away from what the rest state is, but it doesn't have a damping force. It doesn't slow you down as you get back to where you were. You keep going. You get the restoring once you overshoot and come back. So this thing is just going to keep going back and forth, conserving potential vorticity, just as you would if you were a weight on a spring bouncing back and forth. So this process of going back and forth has a rectified effect. As you go north, you get spun one direction. You're always going to get sheared so that the sense of the shear is going to be clockwise. As you go south, the sense of the shear is always going to be anti-clockwise. So if you're fluid at the initial location, at that initial point, you're experiencing westward shear above and westward shear below. You're always experiencing shear to the west. And so you're actually going to start to propagate to the west. Right, so the combination of this oscillation back and forth and this westward shear that's happening at that point at your initial location is going to lead to the generation of these planetary Rossby waves, and that's what they are. They're westward propagating waves that sort of propagate to the west, bouncing about their original latitude. Now, as I've described it here, I've kind of made it like what Michael was suggesting. It's a single point, a single column of air that is sort of moving around, and you might think of it as if it is, draw some sort of analogy between the conservation of planetary potential vorticity, conservation of angular momentum, and a figure skater who draws their appendages in and spins faster. It's a little bit more complicated than that. So the atmosphere is continuous, like fluids are continuous. The atmosphere is continuous and turbulent and messy, and these perturbations happening on all different length and time scales. And that fluid that gets moved northward initially gets replaced by fluid from somewhere else. And that fluid that comes in to fill the void is now perturbed as well. So this process is happening in this sort of continuous framework that if you needed to think about it in terms of some sort of choreographed activity, it would be closer to a messy crowd at a rock concert trying to do some sort of unison movement as opposed to an isolated figure skater. Okay, so that's what we've got so far. That's the basic physics of Rossby waves. They're a consequence of the conservation of potential vorticity. They're always going to propagate westward, even in the northern hemisphere. They're always propagating westward. They occur on all length scales and time scales. So these perturbations that I'm talking about can happen on any, it can be, it can be the sun coming up and heating up the air at one point. It can be air moving over a mountain. Whatever your perturbation flavour is, these perturbations are happening on every time scale possible. The wave speed of Rossby waves is great. It's awesome. The wave speed is dependent on their wavelength and on their frequency. And because we're exciting these waves, we're perturbing these waves on all different length scales and time scales, the wave speeds span a spectrum of speeds. So that if you've got any, but they're always going to be west. So if you've got any eastward flow, chances are you're going to have a Rossby wave that is stationary, standing relative to that eastward flow. So this gives an opportunity for energy to actually start to concentrate and select at this particular length scale that we're seeing here. So the energy that's coming in to feed these things is, it's coming in at the mesoscale. It's coming in at all different scales, but all that energy tends to concentrate at this one particular scale. Right? So that's one of the really neat things about Rossby waves. So they sound relatively simple. They dominate our weather, our lifestyles, our existence. They're incredibly important for renewable energy generation. These things are dependable. These are the things that we're going to rely on. These things are huge. These waves, these winds want to be zonal. They want to be east-west, but there's meanders in there. Those meanders contain an incredible amount of energy. That's the energy that we're actually trying to tap. So we need to know where these things are going to be now, but we also need to know where they're going to be in 50 years' time when we build plants that try to suck energy out. Are these waves going to be in the same place? Are they going to have the same behaviour on the lifetime of the life scale of a wind generation facility? Also dams, these things are bringing water. These things are bringing a lot of moisture. These are the elements that give us our climatological rainfall that we're It's just as important to know when the interruptions to power generation are going to happen. Equally as important as the initial generation itself. Okay, so how do we actually go about studying these Rossby waves? So the primary approach that we've got is to use these reanalysis products. So reanalysis products are observations-based products. They're a retrospective reconstruction of historical states that are produced by assimilating observations into general circulation models. Right, so what that means is that they've got general circulation models, GCMs, running in the background, and they use those to fill the gaps in between the observations. They have physics, but they will respect observations more than they will respect physics. So they will not conserve energy, mass, volume, rain, momentum, or potential vorticity over, like they'll get the observations right before they attempt to like keep the dynamics right. Regardless, they're actually really, really useful. So recent examples of what we call like gold standard for Rossby Wave investigations is one by Michael Barnes recently, which it trawls through reanalysis and identifies distinct events that have happened. These are Rossby Wave breaking events by some sort of specific shape or structure that's happened in the potential vorticity fields, and it performs a composite average of all of these events. So the features that are common to all of these events survive this averaging process. So what we're looking at here are actually an average of 13,000 different events that have been identified in the reanalysis record. What doesn't survive this process is things like the time that these events happen or the location that these happen. These are all centered about some ground zero, and we're looking at east and west, north and south of that particular event at that particular time, whatever time of the year that was. So it's an impressive sort of approach to studying these waves, and it can be used to, once you identify when these events happen, is to go back in time and sort of see what are the conditions are that precede those events, and think about things like rainfall or other atmospheric dynamics that you're actually interested in seeing. But it's reanalysis, so it's hindcast only, it's only of observations, it's only of our record, so we can only sort of try to understand events that have already happened. We can't use these to predict what's going to happen in the future, how things are going to change. For that, we actually need models like climate models that are actually able to represent the processes that we're trying to understand. So, I keep coming back to this figure, this video. I think it's actually pretty cool. The generation scale of these Rossby waves is about the mesoscale. So it's about the length, the length of the distance that something travels in a day. So the sun comes up, starts warming up some air, perturbs it, and then the sun goes down. The distance that's travelled is the scale at which this system is being forced. That energy goes up to the propagation scale, which is the scale of these waves. It's like the size of the continent, and there's several of these waves around the planet. So this is the planetary scale, that's the propagation scale. Energy is always coming in at the mesoscale, and it's always going up to the planetary scale. But where does it go then? Like, the planetary scale isn't getting more energetic. There is some dissipation that's happening, and how the system is dissipating is by these waves actually breaking, these waves getting enough curvature to actually overturn and break. And those processes include things like the generation of fronts, the convection, rainfall, really small scale processes that actually are important for taking the energy out of the largest scale. So we've got the planet, the generation scale being about 100 kilometres, propagation scale reaching up to 10,000 kilometres, and the dissipation scale being about 1 kilometre. So we're literally talking about a kilometre scale numerical simulation that's sitting at, on the size of the planet. So we might be able to do that. We can't do that currently in this country. Other countries can do kilometre scale numerical simulations, but they are horrendously expensive, and really what we need is alternative approaches. So we have an alternative approach in the lab downstairs. So this is our large rotating annulus. It's got, we're able to control the rotation rate, we're able to control the temperature difference, we've got a little bit of topography that we're able to move. It's probably easier to see it in action. This is an example of a case where we're looking down onto the table in the table frame of reference. So the topography looks like it's moving relative to our frame of reference. And there's dye coming in from a little injector that sits at that bit of topography. What we're seeing here, these are our Rossby waves that are sort of moving around the table. Most of the analysis that we do is in the frame of reference of the topography. So quite often most people aren't comfortable with the idea that mountains move. So we try to do all of our analysis in the frame of reference of the topography. All of a sudden, this starts to resemble something more like what our intuition is being like telling us this is what Rossby waves are. So these are the waves in the lee. These waves are traveling west. They're always traveling west, and the flow relative to the topography here is traveling east. Okay, so this is southern hemisphere oriented. So that's the optical camera. We've got a thermal camera as well, which we use as our primary sort of source of diagnostic, and you can kind of see these waves that are in there in the thermal camera. This is in the frame of reference of the table. I can take the temperature fields in this frame of reference of the table, take a long-term average to pull that out, and now I've got the temperature anomalies, which are our sort of hots and colds that are still like being dragged around by the bit of topography, which is about there at this point. And you know, like I said, all of our analysis that we really want to do is going to be in the frame of reference of the topography, so we rotate the images that we get, and we end up with our standing waves, standing relative to the topography, which we can then go through and take a time average of this field to get a surface temperature anomaly, a mean of the surface temperature anomaly. These are our standing waves. These are our, you know, this is nice mode, or wave number 6 probably. You can kind of see some decay in there. So we've got this cool apparatus, and we've got the ability to make waves and break waves, and really we've got all these different parameters that we can change, and we're kind of entering into the space where we are the first humans to actually be able to repeatedly create waves, break waves in this particular way. So what is the first thing that we tend to do as soon as you enter into some sort of brand new parameter space is just turn every knob we possibly can. So this is what we're doing. So what I've got on the top here is just the speed, the differential rotation speed of the topography. So this is going from like westward flow to eastward flow, and what I've got on the y-axis is sort of going from we're changing the temperature difference of the sidewalls, going from sort of a cold outer to a hot outer. These are all just snapshots, individual snapshots, like taken at 1 second interval. There's a lot of dynamics going on in there. Like there's all this structure here that's common throughout all of the different experiments. There's scales that are at the geostrophic scale, which are tiny, and then there's scales at the planetary scale. If we take a time average through this, like what I've just kind of shown, is we can actually start to see the anomalies that are standing relative to the topography. So in our eastward flowing cases, this is where we have waves. In our westward flowing cases, we don't have waves, which is great because we can't have standing waves on westward flow because they're not, Rossby waves only propagate west. So we've got this case where we've got waves, and we can kind of start to see that the standing wave length is dependent on the flow speed, which is also something that intuitively should make sense. If we've got this wave that's bouncing about at some frequency, and the period of this oscillation depends on the spring coefficient of our background potential vorticity. What we're seeing here is actually the distance that the flow is moving in one oscillation. So as we go faster, this flow is moving further in time. So this all agrees with theory, and it makes intuitive sense to what we're doing. But there is heaps going on here, and we really need to start to identify areas of our vast parameter space where there's low-hanging fruit, where there's interesting science to sort of tackle, interesting questions. And I mean, we're trying to eat an elephant, and it's just one bite at a time here. So what I'm going to do is focus on this quadrant of parameter space. We're just looking at eastward flowing cases only that have hot outside temperature and a cold inside temperature. And we're going to ask the question of what happens when you change the temperature. Literally, the simplest question, what happens when you change the sidewall temperature? The motivation for this is a long-standing open question in climate dynamics. So we know polar amplification is happening. We can actually see polar amplification happening. It's where the temperature at the poles is warming faster than the temperature at the equator. So the temperature difference between the poles and the equator is actually decreasing. So in our tank, that's equivalent to changing the temperature difference between the inside and the outside sidewall. The reason why this is an open question and why it has been for a couple of decades is because we don't have a way to test it. We don't have models to test it. Sorry, the question is, like the facts are that the temperature difference is changing. This is going to lead to a slowing of the jet streams. The question that we don't know is, will these jet streams that are now slower have larger north-south waves, like larger meanders, or not? Like that's literally where this science is up to in terms of, if they do have larger north-south variations, if a slower jet is able to go further north and further south, it's going to be dragging more Arctic or Antarctic air to the tropics and vice versa, larger extremes. So that's the question we want to address, and we have the ability to address that with our experiment because we can separate and individually control these different parameters in a way that can't be done with numerics or otherwise. What I'm showing here is the speed of the background flow going from faster to slower. This is the direction that it's going, and the question is, are these waves increasing? So the answer is no, they're not increasing as we go slower, and if anything, they're decreasing. The second question is does the temperature difference between the sidewalls actually make a difference? And in this frame, what we're seeing here, these standing waves, it doesn't make a difference. Okay, so what is this temperature difference doing? So if we take a look, if we think about dynamically what the temperature difference is doing, is it's stratifying the fluid. It's taking, it's increasing the strength of the vertical density difference. This is the large temperature difference case. This is stratified. This is where we are at the moment. The large scale features are still there, but it's pocketed by all this really small scale. This small scale stuff is mesoscale. This is storms. This is weather. This is time dependent, like transient stuff that disappears once we do those long-term time averaging. The large scales are still there, and you can see them. So when we go to the smaller temperature difference, all of that small scale stuff, all of that stratified dynamics disappears because we're now in an unstratified state. The large scales are there, but all the small scale stuff is gone. So what that tells us is that the storms are going to disappear as we go to smaller temperature differences. That's what our lab experiment is telling us. Does that mean that's a good thing or not? Well, these large features are heat waves. These large features are cold spells or droughts. Like these are the longer term extremes. Those extremes will be less extreme because the temperature difference is less, but only by a small amount. So this is one of the things that we can, one of the questions we can ask with our tank. Another one is, what's the difference between northern and southern hemisphere? So so far we've been focusing on southern hemisphere processes. I would say we've been focusing on southern hemisphere processes, and it's because when you look at the main difference between the north and the south, the biggest difference that we've got is that there's more land in the north and more ocean in the south. In potential vorticity space, what that means is that there's more potential vorticity variations in the north because there's more mountains than there is in the south, where there's no PV in the south because it's all just flat ocean. I can show you that in a ridgeline plot, and hopefully you can identify the continents here, the countries. Dynamically, what we're actually interested in is what does this look like when we come at it from the west. So now we're traveling as a jet stream, and we're trying to navigate our way through our potential vorticity gradient space, right? In the southern hemisphere, there's this wall of Antarctica. That's amazing. No PV gets across this. Yeah, that's interesting. There's the Andes. They're huge, and that's what we've been doing so far, is a single piece of topography, just like trying to navigate its way around the Andes. In the northern hemisphere, there's a lot more going on. There's the Rockies here. This is Greenland. That's actually quite huge. Himalayas here. Try to pick your way through there as you're a jet stream and you're conserving potential vorticity. So that's what we're doing next. This is something that Andrew is working on with me at the moment. We're literally just adding an extra bump or two or three into the topography, into the tank, and asking this question of, can we excite Rossby waves from multiple sources, and then how do they interact? So we've got 4 bump configuration cases. The single bump, this particular case, this particular point in parameter space that we're exploring is a wave number 5. That's great. As we go to wave, second bump, it still kind of looks like wave number 5. As we go to 3, you can start to see that the topography itself is imprinting onto the dynamics here. By the time we get to 4, it's well and truly, we've lost dynamics. The system here is now following topography. There is no maths to tell us when this is going to happen. When does the system stop respecting dynamics and start following topography? That's the question that we are interested in. And yeah, there is no maths for it, and there's no numerics that are able to actually sort of start to attempt to do this. Another obvious parameter to explore would be the separation distance between these bumps, and we can quantify it essentially by the number of waves that we're separating the topography by. So, this is a 0 wavelength separation, so it's just a single bump. This is 2 wavelengths, there's a bump here and there's a bump here. When you look at the integer number of wavelength separation cases, they all kind of look the same, which is telling us that, there might be a little bit more going on, but they're basically the same. When you look at these half wavelength cases, we're actually seeing the cancellation of the Rossby waves, this interaction that's like taking the energy out from our wave and somehow cancelling it. But it's not just eliminating it, it's putting it into much, much larger scale features. Remember, these bumps are tiny compared to our domain. This is one bump here and one bump here, and it's making a feature that is half the globe, half of our domain in size. So it's telling us that there's actually wave-wave interactions here that, again, we are very interested in understanding. So, okay, I'm going to quickly go through this. Seasonality is one thing that we're also looking to do. So right now, everything that we've done up to this point is with the steady flow, steady forcing. One thing we know about the planet is that it's never steady. It's always in a transient, and it's not just the transient that we're experiencing, this long-term, unprecedented, rapid climate change. It's also the seasonality of the system. It's always going from summer to winter and back to summer again. Our summer state is like mode number 3 or 4. Our winter state is much messier, mode number 8 or 9. How does the system get between these different states? Like, how do we actually make Rossby waves and break Rossby waves? Because that's what we're trying to do when we're changing the mode number of the system. When we've done our steady cases, we can kind of see, like, we can get a mode number 9 and it's very well behaved and steady, and we can get a mode number 5. Say this is our winter state, say this is our summer state. This is telling us that our autumn state and our spring state are going to be the same because we're just transitioning between these two. But we know that spring weather is very different to autumn weather. So that's one of the questions that we're going to start to look at. So we've got the ability to vary our topography speed, which is our background flow speed, and take it from a summer state to a winter state. We get a couple of extra parameters to play with there. We get the amplitude, and we also get the length of our year, like our duration of the year. And when we just try it, like, we've got a knob to turn, so we're just going to try it. So, we can go from wave number 5, which is what we've got here, and start to slow the system back down. Like, the rotation rate of the table is constant. What we're doing is just changing the background flow, the speed of the topography. We get to this point where we get a double jet that happens, which is amazing. We get a breaking wave right here that happens every spring, which is also incredible. We can predictably break Rossby waves, which is something that is just, it's literally unheard of at the moment. So this is where we're wanting to go. We've got the ability to make these daily snapshots. This is a case where it's not quite able to adjust its dynamics at each time of the year. So, okay, so I'm gonna go through what this is quickly. So I'm looking at daily snapshots here, and we're going from summer, from what that was, like slowing down through to winter here, and then going back up to summer again. And I would call this an intermediate period, like an intermediate duration year, in the sense that it's not quite able to adjust dynamically. Like, we're changing the year too suddenly for the system to adjust to become stationary wave number 7, like the intermediate case. Because we're varying the length of the year, we need to be able to sort of call something common across the year. So, I can take the length of the year and divide it into 12 and call them months, or what I'm doing here is taking it and dividing it into 24 and calling it fortnights. So what you're looking at here is fortnightly snapshots from the summer solstice through to the next summer solstice. And when we've got a short period, like a year that is maybe 50 days in length, you know, the system is rapidly trying to adjust from wave number 5 to wave number 9 quicker than what it's actually dynamically able to do. So it just kind of sits somewhere in between, sits at wave number 6 or 7, and it just kind of hangs out there. It's, you know, the seasonal cycle is just noise on the background of this thing. In the other extreme, we've got, you know, the system able to adjust at all wavelengths, to all seasons, and then we've got something in between, which is, you know, probably where we are on Earth, but we don't actually know that yet. So, future plans for what we want to do. You know, we've done this kind of, you know, we're working through multiple pieces of topography and seasonality. The obvious step is going to be to combine those two. So we've got a case where, you know, we've identified parts of parameter space where we've got waves that cancel. But if we've got a seasonal cycle, that's actually only going to be true for one part of the year. So do we actually have these cases where we've got cancellation of Rossby waves, but only on, you know, autumn, as it's like coming from large scales back to small scales or that sort of thing? In the interest of time, I'll just, we've got plans. We want to do more in the energy space, like explore reanalyses to try to find the signatures of these processes and try to figure out like the energy production implications for that, like steady winds and clouds and precipitation. And then, you know, we would like to be able to help make the next generation of parameterizations for these processes. You know, we're still a couple decades at least away from being able to run, you know, Rossby wave energy, explicit energy through our numerical simulation. So we're going to be relying on parameterizations for that for some time. Other ongoings in the lab. So Callum mentioned these. I'll just leave them up here. We've got sea ice thermodynamics. You know, we grow sea ice and sort of measure it at very, very high resolution and try to understand how the heat is being transported through the sea ice. TiVo's running an awesome ENSO experiment in the tank. We get, you know, a very long tank, 2 layers in there, blow some wind over the top, start to see these kind of ENSO processes. Isostream interactions, that's ongoing and about to go back onto a rotating table. Cool, I'll leave it there. I'm happy to take questions, please.
Questions? Yeah, Nicola.
So I guess you showed this result that we're going to have less storms, right? I'm kind of wondering whether you have any idea of what that means for things like weather and like this idea of weather as a resource. Are less storms like more sun, so that's good, or is it like less water and less wind, so bad? Or has anyone looked at that?
Yeah, I would say so. So I would say it's more predictable. So it's good for weather power generation. The storms will become longer lived. They're going to be these features that kind of stick around for a long time. But the transient stuff that is really difficult to predict is what's actually being eliminated in that in this tank. So.
Roger. I have a very basic, probably embarrassing question with the same models. Can you actually go back to the visualization because it's pretty cool?
The double one?
The different delta T from this. So play it.
Yep, it's coming.
Not as cool until we play.
Yeah.
So the one on the left, at least to a non-climate science eye, you would say there's mixing less.
Yep.
And you're saying there's more storms in the one on the right and less storms in the one on the left. And they have different temperature boundary conditions. What is happening to the temperature across the domain? I'm asking because you've motivated this by a change in the delta T between the equator and the poles now.
Yeah.
Does this lead to a positive or a negative feedback on that? Or is it not at all related?
This is going to be a break. This is going to be an impedance on the ability of the atmosphere to transport heat latitudinally. So this is, if you just think about heat as a tracer, and the green dye is the tracer, this case is able to get green dye from where it's coming in, anywhere in the tank. This one is not. This one's just trapped the green dye, and this jet is actually a potential vorticity barrier that's preventing heat from getting across. So where does the heat go in that point?
Yes,
it's still got to be accommodated.
Does it start to counteract the poleward warming that we're seeing, or amplify it, I guess is the question.
Yeah, it's got to find somewhere else to go. And so what we're showing here is one layer in the atmosphere. There's another layer in the atmosphere where it can go, or there's the ocean where it can go. But what we know is that the radiation balance, the radiation budget, and the deficit between the poles and the equator will be accommodated. It's going to be harder to do it through mid-latitude geostrophic turbulence, which is what is currently dominating the mid-latitude transport of heat at the moment. So we're eliminating its ability to tap into to baroclinic instability to actually perform this task, and we're asking for it to happen somewhere else. This is a temperature condition. It's a Dirichlet condition. So once it's hard to do, it doesn't happen. Right? We're not requiring a heat transport across here. If we swapped one of these with a heat flux instead of a constant temperature, that would get really interesting, and that's in my future fellowship.
In your future,
Yep.
Thank you. Yep.
There's one question from the online audience. The question is, are the result of the two bumps are the different separation, linear, and additive?
Are they linear and additive? Andrew? Andrew is running this one.
With the code I've got so far, I like the energies of the different separation angles seems all be destructive, but maybe I need to normalize the energy difference a bit, because if we have like 10 bumps and like the system is going to be very mixed, and we actually have a lot of energy there. But I'm looking at the anomalies, so maybe for the mixed system there's not much anomalies. So yeah, I'll need to find a way to probe into it a bit more.
We're literally, this is 2 weeks old, those simulations. So we're very actively looking at them at the moment.
Yeah, I also had a question on this animation actually. It's what's happening to the energy of the waves as you increase your delta T, because you mentioned that the circulation gets less stratified, which has to say something about maybe either like how energy is taken out of the waves or is back into the waves.
Yeah.
So is there a point where you lose your waves if you have like too high of a delta T, or?
So where that's a good question. So if we have too large of a delta T, we would get to a point where the stratification is actually in this case the baroclinic instabilities that are able to actually perform this task of getting the green dye outside is this happening on the jet, but as it's doing this, it's also doing this. Okay? And so it's so at some point that baroclinic instability is hitting a resonance, or it's like able to actually interact with some of the processes that are going on out here to actually suck the energy out, suck the heat out. So if we increase the temperature difference even more, then the steepness of this thing would actually lay over more and more. So I think we would probably hit a limit where it's very interesting. We're not there yet. But.
Marcus, I
That's an experimental question. Can you change the dye from green to something else halfway through the experiment, and would that tell you anything interesting?
Yes, I think so. But I mean, the reason why we rely on the temperature is we use this as a tracer. Like the temperature difference in these cases is like 2 degrees. So the temperature difference isn't actually playing any dynamics. The temperature difference is going to drive a geostrophic flow around the tank, but we've got such a small temperature difference that that flow is going to be tiny, like 1/100th of the speed of the topography as it's moving. So what we use the temperature for is literally just for a tracer.
The question about changing the color.
So going back to changing the color.
Old waves mixing with new waves or something.
Yeah, well, these experiments have been running for 48 hours. So there's waves in there. Like it's just we can't see them when before the video starts because there's nothing to look at. So if we took this state and changed the color to red, you'd just see it laid back over the top of the green. Maybe it'd be interesting. Yeah, I think it would be. 3 hours.
48 hours set up, 3 hours of running.
Yeah, if we try to change the outside temperature, it's going to take 24 hours to change the outside temperature. Give it another few hours for the inside to actually feel the outside temperature change. So we get these things spin up to absolute steady state, and then we start like doing the diagnostics on them. Yeah, so the timescale of these things is quite long. But then if we get to like a point where we're looking to take dives through parameter space, if we're at this point and we swap to this point, that adjustment timescale might only be like 2 hours. And at each of these states, we measure for 2 hours. So we can pass through parameter space actually quite quickly. And a lot of it is automated and we can kind of do it remote and that sort of thing. But I can't go this way automated because that's coming in and changing something, like pushing buttons in the lab. So.
But with what Michael said, wouldn't it be interesting to try it for the seasonality?
Yes.
Like to have a different color for each sort of like
More colors.
Yeah.
Good question.
Here's 4.
And put it on t-shirts like those waves.
Yeah.
Elements.
Yeah. Cool. You've given me some very good ideas.
Michael, just a question about climate models that
Yeah.
all the future predictions we have for Southeast Australia is going to get drier, but if these Rossby waves are going to be in the same place, do you worry about that?
So to get a wave, like you need, a certain number of grid cells, to be able to represent that wave traveling. To get the energy that's going in at the mesoscale, we need the grid to be able to represent the mesoscale. For the atmosphere, it's kind of okay. We can get the mesoscale, and we're able to get the planetary scale. But the dissipation scale is where the climate models struggle, is because they're trying to actually curl these waves up. They're trying to curve them. And to get curvature into the vorticity field itself is already a gradient, and then we're looking for curvature in the vorticity field. So it's a second gradient of the gradient field. So if you've got a grid cell that's able to get one thing, and then you want to get the gradient of that, you need 3. If you want to get the gradient of that and the gradient of that, like we're looking at trying to get these things, the curvature of these waves actually requires, 9 or 10 grid cells to be able to do that. So when we say we've got a grid cell that's able to get the mesoscale, which is 100 kilometres, in potential vorticity wave break in space, the effective resolution there is actually going to be more like 1,000 kilometres. We're nowhere near the wave break in space. So there's a parameterization that actually tries to suck energy out at that point. And then the amount of energy that's here at this scale depends on the knob that you've got to turn to get the energy out at that dissipation scale. So are these things in climate models? Kind of, but yeah, like they're heavily parameterized, and we don't actually know what the, like we've tried to parameterize it to match observations, but you know, without actually having guidance on like what are the dynamics that we need to get important. Yep.
So in engineering models, when you have something like that, like an internal rotation that you can't, or a rotation that you can't constrain, you would usually set it as a variable, solve a set of equations for it, and then you apply a sort of constraint that it tries, the variation approach, that it tries to follow the vorticity as much as it can, and then you would have it as a primitive scalar, primitive vector. But anyway, you have it as a primitive and you kind of tie it together.
Okay.
So you can get this gradient. I don't know if people do that.
Me neither. I mean, I just do it in the lab and it's a lot easier for me here. I wouldn't know what to do numerically.
Any other questions? Okay. Let's thank Kyle again. I believe there's cake outside. I think I saw it. Yeah. So enjoy.
One thing, if I may, very, very quickly.